Okay, welcome to this review of complex variables. This review, I'd like to remind you, is just customized to this course ECE 3337 as Signals and Systems Analysis. So I've organized this review in three parts. The first part just introduces you to the basics of complex numbers, how to calculate the angle correctly, a few rudimentary concepts in complex algebra. We define the complex conjugate, and then we introduce Eulers Formula. In the second part of this three-part series, we'll talk about complex functions, and in the third part, we'll talk about how to do calculus with complex variables. Okay, let's get started. Now, complex variables are extremely useful for this course, and because they're extremely useful for analyzing signals, circuits, and systems. That's what we're going to be talking about in this course. This subject is a prerequisite for this course, and it's an important one. That's why I'm making up this review, right? Now, why bother with complex numbers, right? Complex numbers will provide us with important advantages, as we'll see throughout this course. A lot of our formulas will become simpler and easier to understand and easier to write. A lot of our calculations can become shorter and much more intuitive and sort of understandable, right? And there we'll run into, some occasional weird or tricky situations that can be handled cleanly using complex notation rather than, the regular notation in real algebra. Now, it turns out that the field of electrical engineering, it has a lot of language or words that are ultimately rooted in complex variables. So I think this is a subject that we all want to know about, right? What I'd like you to be able to do is to become familiar with this topic of complex variables, learn to take advantage of complex representations. Now, these complex representations are sort of two-dimensional in nature. We'll talk more about that in a second. And that's what leads to some of the simplicity in the formulas, okay? And if you become good at complex variables, I hope that you will avoid some common mistakes, especially on your homeworks and tests and, once you become practicing engineers, maybe in real life. So a couple of caveats are in place. So the subject of complex variables is ordinarily a one-semester course, okay, or maybe more, depending upon how deep you want to get into this. So these three little lectures that I'm recording are not intended to be comprehensive. They cannot pretend to be so, okay? They are not a substitute for a complete course that the math department would offer, for example. What I'm trying to accomplish here is to simply remind you of things that hopefully you already learned in an earlier class, right? And again, I'm just focusing on topics that are directly needed for this particular course, ECE 3337. Now again, I'm not going to be talking about any theorems and proofs and things like that. That level of rigor is appropriate for a math course, but here we're just trying to be intuitive and sort of practical. Okay, so I'm going to be somewhat loose, not so rigorous, and hopefully that'll be adequate for the purposes of this class. By and large, the subject of complex variables is covered very well in books, and here are my two favorite ones, right? The one by Matthews and Howell. I think it's just written in a beautifully simple manner. I just love it. Now, if you have your textbook, it also has an appendix. I think Appendix B covers the subject of complex variables. Now, Schwamm's series has a book on complex variables, the one on your right. It has lots of worked out problems. So sometimes we can learn a lot from seeing how, from looking at worked problems and learning from that. So luckily the Schwamm series book is also quite inexpensive. So I think it's about $10 or something like that on Amazon. So I urge you to have a copy of this handy. And I want to point out that Appendix B of the book is inadequate for the purposes of our course. Okay, that's the reason why I tried to prepare these lectures. Okay, let's start with the basics, right? A complex number, denoted Z, okay, can be thought of as an ordered pair of two numbers, okay, X and Y. Okay, so Z is really a two-dimensional quantity, and herein lies its value, right? So by encoding two different numbers X and Y into a single letter, we hope to later on end up with formulas that are a lot simpler than they would otherwise be. Okay, now Z can also be thought of as the sum, okay, of two numbers, okay, X and J times Y, right? So J is square root of -1. Okay, of course, this is not a real number, so that's why we call it an imaginary number. Okay, so J square is -1. Okay, now in the math department they would use the letter I for square root of -1. Now we electrical engineers like to save the letter I for current, so that's why we prefer to use the letter J to refer to square root of -1. Okay, so now this two-dimensional number, okay, lives in a plane. Okay, the x-axis is X, the y-axis is, of course, Y, and this whole plane is referred to as the complex plane. Okay, now the y-axis is also called the imaginary axis, and the x-axis is also called the real axis. So if I give you any number, okay, in the plane, say x comma y, you can draw a line from the origin to this number, okay, and the length of this line is r, okay, and the angle that this line makes with the x-axis is theta. Okay, so now the length of this line from the origin to the point xy, okay, is also called the magnitude of the complex number. Okay, and it's also written as sort of like the absolute value of z, right, or the magnitude of z. Now the projection of this line onto the x-axis, okay, is really r times cosine of theta, right? And the projection of this on the y-axis is r times sine of theta, okay? So z, the complex number, can also be written as r times cosine of theta plus j times, sine of theta. Oh, sorry, r times sine of theta. Now, the same number, z being x plus jy, since we know, we've defined what an r and a theta is, can also be written in polar coordinates, okay? And we write it as r times e to the j theta, okay? I'll come back to this in just a little bit, okay? As to why are we bringing in this e and there's the j and the theta and everything. This will become apparent to us shortly, okay? And so let's get on with this. Now, as I'm writing all this, you'll sort of notice that, I've been a little sloppy, right? So basically, when I wrote the letter Z, on paper, I just wrote it like that. Whereas, if you look at the slide, it's a bold Z, right? So one of the questions that, it's a very practical question really that always comes up is how do I write these numbers, right? So if you want to distinguish between sort of the regular Z and the bold Z, you can put an extra line to it, okay? We call it the chalkboard version or the whiteboard version of bold, okay? And if you find that notation convenient, by all means, use it. Now, if you look at the complex plane, okay, if you think about the x-axis, you can think of it as a set of all points for which y equals 0, right? If you look at the imaginary axis, the y-axis, right, then you can think of it as the set of all points for which x is 0, okay? So points that lie along the x-axis are called purely real, okay? And the points that lie only along the y-axis are called purely imaginary, okay? Now, for a purely real number, okay, its angle, and we write the angle like that, okay, angle of Z, okay, is 0, okay, because it makes 0 degrees angle with the x-axis. For all of these guys, okay, points along the imaginary axis, the angle of Z is either plus or minus 90 degrees, right, depending on which side you are. If you're on this side, it's plus 90 degrees. If you're on this side of the x-axis, it's minus 90 degrees. Now, these two lines intersect at the origin, and at the origin, not only is x 0, okay, but also y is 0, okay? Now, since both x and y are 0, okay, there is no meaningful angle that we can associate with this point, right? You can have the vector pointing every which way, and you still arrive at the same point, right? So the angle is, essentially undefined for the point at the origin, also known as the 0. Okay, so if you have a point in the complex plane, okay, like I said, you have the r and the theta, right? We use this notation, theta is equal to angle of Z. Now, in computing this, it takes a little bit of care, actually. We need to be a little bit careful. So let me explain, okay, in just a little bit. So before we get to that, let's review some basic trigonometry, okay? The tangent function is the ratio of the sine to the cosine, right? And basically, the denominator, which is the cosine, is going to go to 0 at some, and at 90 degrees, and so the tangent function goes to either plus infinity or minus infinity. The important thing is that it's a periodic function, okay, just like sine and cosine, but its period is different, okay? Its period is 180 degrees or pi radians instead of 360 degrees or 2 pi radians, which is true for the sine or the cosine function. Now, we can also define a function called the inverse tangent. So if you give it a number, it'll give you an angle that's between minus 90 and 90 degrees. So you can think of this as, just one segment of the previous, page basically turned around, okay, by, on its side. So obviously, angles of complex numbers don't just lie in the range minus 90 degrees to 90 degrees. So basically, the arctangent by itself cannot give us the correct angle for every complex number. So it takes a little extra work, and let me explain what's going on, right? So consider 4 different points, okay? So you got the, my pen seems to be drying up, okay? So you got a point here, say 2, 3, okay? Now if you look at its x and y projections, okay, so this is the point 2, 3, right? This is 2, okay, and this is 3, right? So this angle theta, okay, is going to be the inverse tan of 3 over 2, okay, and that turns out to be about 56 degrees, okay. Now if you consider a point which is sort of like a mirror image of this one, okay, on the other side of the axis, okay, this will be like minus 2, 3, right? You'll find that the ratio of this, okay, to this is also about theta, okay, which is 56 degrees. So if you want to calculate the angle of this point, it has to be this whole arc, okay? We call that, so if this point is Z1 and if this point is Z2, okay, and if this is theta 1, then this big angle here is theta 2, right? So theta 2 is obviously 180 degrees, which is this whole thing, minus this 56 degrees, right? So basically by watching the, where on the complex plane, in other words, on which quadrant a point lies, we can, figure out its angle correctly, okay? So the arctangent, in a nutshell, okay, by itself, it can be fooled, okay? Now, another extreme example is this one here. So if I consider the point minus 2, minus 3, right, then, the arctangent of, minus 3 divided by minus 2 is the same as the arctangent of 3 divided by the 2. So the arctangent function by itself, okay, cannot always give you the correct angle. So what we have to do is to use some common sense and say, okay, where is that angle? And in this case, the angle is going to be this. This is the 56 degrees, and we had to figure out how to add 180 degrees to that to get this overall angle like that. Okay. Now, if you want to measure the angle this way, okay, it's, you're going to essentially subtract 180 degrees. Okay. So basically, all I'm saying is that you need to pay attention to where in the complex plane a certain point lies. Obviously, points that lie along the y-axis or the imaginary axis will have an angle of either plus pi over 2 or minus pi over 2. Okay, and of course the 0 point will have a meaningless or an undefined angle. So let's do some basic review of complex algebra. Okay, so let's try. So one of the nice things about complex algebra is that it's kind of simple, right? If you have two complex numbers, z1 and z2, and you want to add them, okay, you just have to add the corresponding real parts, like x1 and x2, and the imaginary parts, y1 and y2. Okay, if you just add them together, you can just add two complex numbers. Okay, now if you want to multiply two complex numbers, okay, it's kind of just like with real algebra. Okay, so z1 is x1 plus j y1, and z2 is x2 plus j y2. If I want to multiply them, right, I'll multiply x1 x2, okay, plus x1 y2 times j, so j x1 y2 plus j x2 y1, okay, and then I'm going to have another term j y1 plus jy2, and that's like j squared times y1, y2, and j squared is minus 1, so I'm just going to write minus y1, y2. Okay? So basically multiplying complex numbers is pretty straightforward. You're just using the fact that j squared is minus 1. Okay? So you can just collect the real and the imaginary parts of this together, and you get the formula that you see on the slide. Now, the complex conjugate of a number, okay, is the number that is sort of reflected with respect to the x-axis, right? So if you have a number z, which is x plus jy, its complex conjugate is indicated by a little asterisk, okay? And we simply negate the imaginary part, so it's x minus jy, okay? So if you multiply, okay, let's do that on the next slide. Okay, so if you multiply a number by its complex conjugate, okay, you just get x squared plus y squared. That's what you see on the bottom of the screen. It's easy to see, it's easy to verify. The real part is x squared plus y squared, and the imaginary part goes to 0. Okay, and x squared plus y squared is simply r squared, or the square of the magnitude of the complex number. Now, if you add the conjugate of a number to itself, okay, the imaginary part kind of disappears, and you just get 2x. Okay, so adding a number and its conjugate together is one way to extract out the real part of a number, okay, and sort of throw away the imaginary part. Now, if you want to divide two complex numbers, okay, it takes a little bit of extra work. Okay, what you have to do is to look at the denominator, right? So if in this case on the screen you'll see that the denominator is x2 plus jy2. I'm trying to divide z1, I'm trying to compute z1 divided by z2, and z2 is x2 plus jy2. Then I have to multiply both the numerator and the denominator by the complex conjugate of the denominator, right? And the idea is that, you're going to make the denominator real, okay? So the denominator becomes, x2 squared plus y2 squared. And if you expand out the product at the top, okay, which is basically z1 times the conjugate of z2, then basically you can sort of collect the terms together and get the answer that you see on the screen. This is easy to do, okay? Now, the important thing to keep in mind is that any time you have a denominator, okay, you have to explicitly pause, okay? It's a good habit. You have to explicitly pause and make sure that the denominator is not 0. Because whenever the denominator is 0, okay, the results of a division are essentially meaningless or undefined. Okay, that's the only caveat here, but by and large, as long as you just follow, the rest of the rules for algebra, okay, just keeping in mind that j squared is minus 1, you should be able to largely get the correct answer. Now, if you want to compute the reciprocal of a complex number, we use the same trick. Okay, so the idea is that you want to be able to express the results as a real part and an imaginary part, right? That's what we're trying to do. So what you do is that you multiply both the numerator and the denominator by the conjugate of the denominator. And when you do that, right, you get the result that you see on the right. Okay, the algebra itself is fairly straightforward, but again, okay, keep in mind that anytime you have a denominator on your hands, you have to pause and take a look and ask the question, okay, is it 0? Can it go to 0? Okay, and keep in mind that when the denominator is 0, the result of the division is essentially meaningless. Okay? So now complex algebra also works, you know, straightforwardly in polar coordinates, except that you just have to expand it out, right? Basically, if you want to add two numbers, right, you just have to write out the real and imaginary parts for each of these numbers and add the corresponding quantity. So add the r cosine theta, which is the real part, together for the two numbers, and r sine theta, which is the imaginary part, for the two different numbers. Now, if you're going to be multiplying two complex numbers, right, then you know, it's fairly straightforward. So it's just like multiplying anything else. So if z1 is r times e to the j r1 e to the j theta 1, and z2 is r2 e to the j theta 2, then z1 times z2 is just r1 times r2 times e to the j theta 1 times e to the j theta 2. Now when you're multiplying two exponentials, right, you basically have to add these two guys, okay? So you write r1 times r2 times e to the j theta 1 plus j theta 2, so I can take j outside common, and that becomes j theta 1 plus j theta 2. Okay? Now division works the other way, right? So if I want to do z1 divided by z2, okay, then I take r1 e to the j theta 1 divided by r2 e to the j theta 2. And before I go any further, I want to sort of remind myself that in case this denominator goes to 0, then this whole thing is meaningless. Okay, can't go any further. But if the denominator is not 0, then I can simply, okay, process this as r1 divided by r2 times e to the j theta 1 minus theta 2. This is just like in sort of normal algebra. Okay. Now there is an important formula that sort of I didn't talk about, and let's talk about that now, right? So this is a famous mathematician. I have a little picture of him there. Okay, it's Euler, right? That's how you pronounce his name, I think. So this gentleman, this mathematician, came up with a formula that has sort of been billed as the most beautiful equation in mathematics. And it's not hard to see why, right? So what he said was e to the j theta, okay, is cosine of theta plus j sine of theta. Okay, so this is a polar representation of a number whose magnitude is 1 and whose angle is theta. Okay, now what it's doing is that it's actually relating some pretty remarkable quantities. Okay, first of all, j being, you know, a square root of -1 is a pretty remarkable quantity in itself. Now e is another remarkable quantity. Okay, and then you got the classic trigonometric functions, cosine and sine, also, you know, widely used and remarkable quantities. So all of these are sort of linked together in one really simple formula. Now, if you replace e to the, you know, if you replace theta with minus theta, okay, so you get cosine of minus theta, which is the same as cosine of theta, okay, and if you look at sine of minus theta, that's minus sine of theta, so we write minus j sine of theta. Okay, now if I add these two formulas, okay, so I say e to the j theta plus e to the minus j theta is 2 times cosine theta, right? So I can divide both sides by 2, and I get a formula for cosine of theta in terms of e to the j theta and e to the minus j theta, right? So, and similarly, I can derive a formula for sine theta. Now, let's talk a little bit about sine theta and cosine theta, okay? These are two functions that we'll be using a lot, in this course, right? So you might as well get to know it, get to know these two functions intimately. Okay, so sine and cosine are periodic functions. Their period is 2 pi radians, which is 360 degrees. So sine of 0 is 0. This is the red curve that you see on your left. Okay, and basically as theta goes up between 0 and pi over 2, which is about 90 degrees, the sine gradually increases. Okay, and then it reaches a high value of 1 and then starts to decrease again, and it goes to 0 at 180 degrees, okay, or pi. And then it then heads off in the opposite direction all the way down to -1 and then finally comes back to 0. And this pattern repeats over and over and over, sort of, infinitely. Now, the cosine has the same shape, but these two curves are sort of offset with respect to each other, right? They're sort of off by 90 degrees, right? So if you take the cosine function and sort of scooch it to the right, and we're going to call it a delay, okay? So if we delay the cosine by 90 degrees, you will get the sine function. Or alternately, if you were to advance the sine function by 90 degrees, you'll get the cosine function. Now the sine and cosine are periodic functions, like I said, right? So they repeat every 2 pi radians, and 2 pi is 360 degrees. So if I add or subtract any multiple of 2 pi radians to the angle, it doesn't change the value, okay? Because they're periodic. The same pattern keeps showing up again and again, right? So the equations here are of course self-evident, but immensely useful, okay? You're going to be using this sort of property quite a bit in this class, okay? So let me show you an example of how some of these things play out. So one thing to keep in mind, of course, is that the sine and cosine functions, they arise quite naturally from a point that's going round and round in a circle, right? So if the radius is 1, we call that a unit circle, right? So if you have a point that's kind of like going round and round and round a circle, then its x projection, or the projection on the x-axis, is sine theta, and its projection on the y-axis is cosine theta, right? And you can sort of easily see why these two functions are off by 90 degrees by using this type of mental picture, okay? Now, if you have, you remember Eulers formula, right? So z is r e to the j theta is r times cosine theta plus j r sine theta, right? So let's suppose that you want to raise this to the power n. Let's say you want to calculate z squared or z cubed or something like that, so any power, right? So basically z is r e to the j theta, and if you want to raise it to the power n, okay, we know that it's like r to the n times e to the j theta n, right? Now if you write this in Euler's formula, it's simply r to the n, okay, cosine of, okay, n theta plus j sine, n theta. And this is a remarkably simple formula, because if without Euler's formula, this would be quite a messy calculation, to say the least. Okay, now if you want to go the other way, okay, so in other words, if you want to calculate the square root of a complex number, or maybe the cube root, or the fourth root or something like that. In general, if you have a number z, okay, which is r e to the j theta, and then you want to basically raise it to 1 over n, which means it's the nth root of the thing. Let's do that on both sides, okay? Then what we get is r to the 1 over n, okay, times e to the j theta over n, right? But just let's pause to think about this, right? So this isn't quite right. So for example, if I say find the square root of 1, right? If I say, what is it, right? It has two possible values, right? So because 1 squared equals 1, and minus 1 squared is also equal to 1. So this is a multi-valued situation. So how do we untangle that, right? One way to untangle that is to simply say that what the formula that we had here is exactly the same as r times e to the j theta plus n 2 pi, right? So if you multiply 2 pi radians by any number n, any integer n, and add it to theta, right? It produces the same answer, correct? So if we look at it this way, so you get r to the 1 over n, okay, times e to the j, okay, theta plus n 2 pi, or k 2 pi, you can use any letter you like, divided by n. Oh, I shouldn't use the letter n, so let me use the letter k here, okay? So this again also gives you all of the square roots or the nth roots of a complex number quite nicely. Now, Euler's formula is first of all easy to remember, and for that reason we can all use that to derive a whole bunch of things. For example, if I forgot what the cosine of a sum of two different angles, say A and B, was, I can use Euler's formula to derive that, right? So e to the j a plus b can be written straightforwardly as cosine of a plus b plus j times sine of a plus b. Then you can also write it as e to the ja times e to the jb, correct? So if you write out these two things using Euler's formula, then multiply it out, what you can do is that you can compare the corresponding terms. In other words, you can compare the real part and the imaginary part. And the reason why we need to do that is because if I give you two different complex numbers, right, z1 and z2, and ask the question, when are these two complex numbers the same? The answer is that the real part should be the same and the imaginary part should be the same. Okay, so if you, following from that definition, if you compare the corresponding terms, you get the familiar formulas for the sum, for the cosine of a sum of two angles, and this, and the sine of a sum of two angles. And by the same exact process, you can also calculate the formulas for the cosine of the difference between two angles, and also the sine of the difference between two angles A and B. Okay, I would urge you to just go through these derivations and see if you can, you get the same answers, right? That's a good sanity check that I think I would urge you to do. Now, if the radius, right, or the r value is a 1, then what we get, is called a unit circle, like I mentioned earlier, and the unit circle is kind of something that we will encounter frequently, and one of the interesting things about a unit circle is, its magnitude is 1, so you can ask yourself the question, what are those nth roots of 1, right? And they'll all lie along the unit circle. So anyway, there are going to be some angles that appear so often that it's useful to sort of remember what's going on there, right? So if theta is 0 degrees, right, we're talking about e to the j theta, okay, being e to the j 0. Now anything raised to the power 0 is a 1, right? So you can think of 0 degrees as the number 1, and it makes sense because the real part is 1, which is what's along the x-axis, and the imaginary part is 0, right? So it makes total sense. Now if you look at the point in the middle, right, at 45 degrees, then it's e to the j pi over 4, right, because pi over 4 is 45 degrees, and you can draw a triangle there, and use Pythagoras theorem, right? And you can see that it's you know, the x component is 1 over square root of 2, and the y component is 1 over square root of 2. Similarly, right, a point at 90 degrees is a purely imaginary point, okay? So its angle is 90 degrees, so the cosine of 90 degrees is 0, and sine of 90 degrees is a 1, so the number is just j, right? So e to the j pi over 2 is just j, right? And that also makes total sense. Similarly, if you look at the point at 180 degrees, you know, it's basically e to the j pi, and it's minus 1. It's on the x-axis, but on the negative side. Now you can also get the same answer when it's minus 180 degrees. So e to the minus j pi is also equal to minus 1. And likewise, when theta is 90 degrees, okay, the point at the bottom, then e to the minus j pi over 2 is minus j, right? It's a purely imaginary number. And when theta is minus 45 degrees, right, you get the complex conjugate of the number that's like the at the top, which is when theta is 45 degrees. Okay, so the two numbers are the same except for the imaginary part has the opposite sign. That's the complex conjugate. So to summarize, complex variables are extremely useful, and a lot of their utility comes from the fact that they're two-dimensional in nature, right? So these are numbers that live in the two-dimensional complex plane rather than on a single one-dimensional line. I love Eulers formula. It's you know, in my opinion, and certainly in the opinion of many, one of the most beautiful equations out there. I think it's right on par with E equals mc squared. Okay. I think it's helpful to develop some intuition and a mental picture of this equation. You need to certainly memorize this equation. Okay, it shouldn't require a crib sheet. But if you have a crib sheet, put it on that. Anyway, just for good measure. We need to be careful in calculating angles, right? Because points, you know, you have to pay attention to what quadrant it's in or what axis it's on, and in order to get the correct angle for a complex number. We talked about the notion of a complex conjugate, and we went over several operations related to complex algebra. For the most part, they're very similar to ordinary algebra, except for the division and the 1 over z, right? Now, in both of these cases, you really need to pay attention to the denominator. Make sure it's not 0, right? Because if it's 0, you know, it's meaningless. It just doesn't make any sense. Now, one of the things I'd like to you know, mention is that you need to make some time for ECE 3337 on a daily basis, because we're going to be using quite a bit of math, and you need to sort of keep your math skills you know, in good shape. And you know what, math is just like any sport. You know, if you're a runner, you know, you have to run frequently, right? Or if you do some other sport, you have to practice on a daily basis. Or like dance, you know, you got to, you know, you do your dance practice on a daily basis in order to stay fresh. Math is not a spectator sport. I think that, you know, watching this lecture is simply not going to be enough. I think you should take that Swamp Series book or anything else, in any other textbook that comes in handy, and just do some problems, right? It's only by doing problems that and running into mistakes and then figuring out your way that you will really, you know, really get this material. And you know, try to just grapple and understand the basic principles. Don't just memorize some recipes blindly, right? Doesn't help. Try to get a real intuitive feel for it. And once you get it, it's going to be so easy, right? If you don't get it, it's going to be like horrible and hard. So always ask questions, seek answers, and like I said, try to understand the fundamental principles. And you know, if you don't get it once, try again, you know. and go at the book all over again, and you know, with some repetition, you're going to get it. Like I said, math is just like a sport, actually. Okay, thank you.